So last time we were looking at this insertion sort algorithm. So the idea is you'll maintain a sorted portion and unsorted portion and go through the iterations. So in each iteration what we'll do is we'll take up the first element in the unsorted portion, and that is said to be at index I, and we'll try to insert it somewhere in the appropriate location in the sorted portion. So by running a J loop, that will go from I minus 1 all the way to 0. Okay. Now it depends on the value of the element at index I. If the element at index I is the smallest or is lower than all the elements in the sorted portion, then we have to go through the J loop all the way up to index 0. On the other hand, if the element at index I is greater than all the elements in the sorted portion, we don't need to run the J loop beyond the first index I minus 1, because if say this is say 70 or something, then 70 will be greater than 45, so there's no need to check further down because this is a sorted portion. If 70 is greater than 45, it's going to be greater than everything else to the left of 45. So that's the idea here. So we looked at the best case time complexity, and so that will happen if the scenario is like what I just said. If the array is already sorted, if the input array is already sorted in the increasing order and the values are increasing from left to right, then for every element at index I, you need to just do one comparison and the J loop at index J equals I minus 1. So that means for every index I, the J loop will run only once. So that is given by a summation which I showed last time. Sigma I equals n minus 1, and the J loop will run only once, which is 1. So it is in the upper limit minus lower limit formula. N minus 1 minus 1 plus 1 minus 1 plus 1 will cancel, n minus 1. So that's the best case number of comparisons you do for insertion sort. Now for worst case will happen where if the array is reverse sorted. So if the array is reverse sorted, means something like so if it is like this, then every time we have a sorted portion, say something like this is our sorted portion up to say this, and then we have say the unsorted portion like this. Then if I want to insert 10, I have to go all the way to index 0 and then do the insertion. So that's why in the worst case, if the array is reverse sorted, then you have to run the J loop all the way from I minus 1 to index 0. So that can be given by this summation, sigma J equals I minus 1 to 0, and then I runs from 1 to n minus 1. So inside the J loop, we'll do for any particular value of J, we still do only one comparison, comparing the value of V, which is the value of the element at index I, with the value at index J. So before we proceed to solve the summation, we should kind of adjust the limit, because the lower limit I minus 1 is greater than the upper limit, which is 0. That's because you are running the J loop from on the backwards, from I minus 1 to 0. Since you run it backwards, it is like this. But you see here inside the J loop, you just do one comparison, and it doesn't depend on really J. So you could really swap or flip the limits. So the J loop could be considered to run from lower limit 0 to I minus 1, so it doesn't really change the final result. So then we have a constant inside summation, so you can fits within the upper limit minus lower limit formula. So I minus 1 is the upper limit minus 0 plus 1, and that is negative 1 plus 1 will cancel. This is sigma I equals 1 to n minus 1i. So this is like a summation 1 plus 2 plus up to n minus 1. And 1 plus 2 up to n minus 1 can be written as one plus 2 up to n minus 1. So think about this like 1 plus 2 plus 3 up to n is going to be n times n plus 1 over 2. Instead of capital N, you have n minus 1, so it's n minus 1 times n minus 1 plus 1 over 2. So this is the worst case number of comparisons. So the worst case is this, best case is n minus 1. They are different from each other, so you have to use a big O notation of worst case. Now the worst case is n minus 1 times n over 2, so that's going to be n square. That's the most dominating term. Okay, any question on this? Okay, so let us now look at the average case complexity, in the sense that on average, so far we focused on best case and worst case in most of the algorithms so far. So let's take up this algorithm to also analyze the average case time complexity theoretically as a function of n. Most of the time it's difficult to analyze theoretically the average case complexity. That's why we resort to the programming approach, as we'll do in the programming projects. You will run several iterations, measure the runtime, and then average the result that you find. But for insertion sort, it's relatively easy to analyze the average case complexity. So let us see how to do it. So on average, we will run the J loop through half of the sorted portion. Okay, so in best cases we'll run only from j at j equal to I minus 1 and stop there. Worst cases we'll run j equals I minus 1 all the way to 0. So on average we can say we'll run the j loop from index I minus 1 to index I minus 1 over 2, so somewhere in the middle of the sorted portion. And again, still for each value of j, as we go through, we'll do just one comparison, comparing the value of v with a of j. So the summation can be written like this: sigma I equals 1 to n minus 1 and j equals I minus 1 to I minus 1 over 2, 1. So again here the lower limit is I minus 1 and greater than the upper limit I minus 1 over 2. But since there's just a constant independent of j inside the summation, we can flip the upper limit and lower limit and write it as I minus 1 over 2 to I minus 1. And that falls within the upper limit minus lower limit formula. So I can say then it is something like this. I did not show the work, but let me do it here. Okay, so what we have is I equals 1 to n, and the inner summation loop runs from j equals I minus 1 over 2 to I minus 1, 1. So we can apply the upper limit minus lower limit formula here. We will keep the outer summation as it is. And the inner summation, if you apply the formula, it is upper limit I minus 1 minus a lower limit I minus 1 over 2 plus 1. So this is like some x minus x over 2 plus 1. So we can say that is x minus x over 2 is simply x over 2. So I equals 1 to n I minus 1 over 2. So I'll write it like this. I minus 1 over 2 plus 1. And that's what I have shown here. I minus 1 over 2 plus 1. Now the I loop will run from 1 to n minus 1 because that's the maximum index, right? So let me make the change here. So I loop will run from 1 to n minus 1. Okay, so we can solve this summation further by writing it as sigma 1 to n minus 1. So I minus 1 over 2 plus 1, if you simplify it, we'll take the LCM 2 as the common denominator, I minus 1 plus 2. So this is how you can, so I minus 1 over 2 plus 2 over 2 is 1. So I can take 2 as the common denominator and write it like this, I minus 1 plus 2. So I can take this 1 over 2 all the way outside as a constant and write this as summation I equals 1 to n minus 1. So the numerator is I minus 1 plus 2, so that is simply I plus 1. Okay. Now we could expand it further. So let us do that as a practice. So it's going to be 1 over 2. Now one way to handle this summation like this is, we have I plus 1 sigma equals 1 to n minus 1. So you can substitute the different values of I and see how it comes out to be. So that's going to be so if I equals 1, I plus 1 is 2, I equals 2, I plus 1 is 3, plus so on, I equals n minus 1, so I plus 1 is going to be n minus 1 plus 1, so n minus 1 plus 1 is n. So here we can say the is like 2 plus 3 up to n. So I am going to add a 1 and subtract a 1. Okay, so that's going to be, so because I'm adding a 1 and subtracting a 1, then now I have, this is 1 plus 2 plus up to n, and that's going to be n times n plus 1 over 2. So n times n plus 1 over 2 minus 1. So if you simplify this further, you will basically get n square as the most dominating term. So you can even leave it as it is and just say this is proportional to, so let us do one more step. Okay, so that's going to be n square plus n minus 2 divided by 2. So now asymptotically, as n increases to infinity, what we can say is this is n, we can discard all the lower order terms and keep only the higher order term. So this is 2 times 2 in the denominator, so that is 4, and discarding all the lower order terms, you are simply left with n square. So this is what I want to illustrate. On average case also, insertion sort is an n square time complexity algorithm. So the best case was n minus 1. The worst case is like n square, and on average is also an n square complexity. Okay. So basically we have double summation, and as you work it out, so if the inner summation is the upper limit minus lower limit plus 1 formula, and we just simplify it to get this, expand by substituting different values of I, and just do some math adjustment to simplify this summation. Okay, so add and subtract minus 1. Since you're adding and subtracting minus 1, now we can get 1 plus 2 up to n, that is n times n plus 1 over 2 minus 1, and just simplify it to ensure that this is still an n square expression. And so that's what we want to show. On average also, insertion sort is an n square time complexity algorithm. Okay, any question? All right, we'll stop.